In the previous modules, we went through the steps of asking the right question and preparing our data. In this module, we'll go through the process of selecting algorithms. We will use our problem knowledge to help us decide the algorithm to use. More specifically in this module, we will discuss the role of the algorithm in the machine learning process. Select our initial algorithm by utilizing the requirements identified in the solution statement as a guide, and discuss at a high level the characteristics of some specific algorithms. Finally, we will select one algorithm to be our initial algorithm. Notice that I said initial algorithm. As mentioned previously, in machine learning we often cycle through the workflow. In our search to find the best solution, it is likely we will need to train and evaluate multiple algorithms. It is important that we understand the role of the algorithm in the machine learning process. So let's review how the algorithm is involved in the process. One could say that the algorithm is the engine that drives the entire process, and we will see this illustrated as we walk through the process of using the algorithm to create and use a trained model. For our prediction problem, we will use training data containing examples of the results we are trying to predict and the feature values we are using to predict that result. When the training function, often named fit in scikit-learn, is called, the algorithm executes its logic and processes the training data. Using the algorithm's logic, the data is analyzed. This analysis evaluates the data with respect to a mathematical model and logic associated with the algorithm. The algorithm uses the results of this analysis to adjust internal parameters to produce a model that has been trained to best fit the features in the training data and produce the associated class result. This best fit is defined by evaluating a function specific to the particular algorithm. The fit parameters are stored, and the model is now said to be trained. Later, the trained model is called via a prediction function, often named predict in scikit-learn. When this prediction function is called, real data is passed to the trained model. Using only the features in the data, the trained model uses its code and parameter values set during training to evaluate the data's features and predict the class result, diabetes or not diabetes, for this new data. Now that we understand the role of the algorithm, let's select our initial algorithm. Since machine learning can be applied to a lot of problems, there are a lot of machine learning algorithms available. A quick check of the scikit-learn library shows that there are over 50 and more being created. So how do we decide which algorithm to use? To decide which algorithms would be suitable, we can compare the algorithms on a number of factors. Not surprisingly, data scientists have different opinions on what factors are important in selecting algorithms. The decision factors presented here represent one possible set of factors. As you gain experience, you will likely develop your own set of factors and decision criteria. For our example, we are going to use these decision factors to select our initial algorithm: what learning type they support, the result type the algorithm predicts, the complexity of the algorithm, and whether the algorithm is basic or enhanced. We will use our solution statement and knowledge of the workflow to help guide us in the evaluation of these factors. Each algorithm has a set of problems with which it works best. One way to divide them is to look at the type of learning they support. With that in mind, let's go back to the solution statement and see what guidance it offers. Reading the statement, we see that our solution is about prediction. Prediction means supervised machine learning, so we can eliminate all algorithms that do not support supervised machine learning. That reduces the number of choices, but we still have a lot. Let's see what else we can do. Let's see how the result type can help. Prediction results can be divided into two categories: regression and classification. Regression means a continuous set of values. Back in our example of determining the price of the house, we used the features of the house, size, number of bedrooms, etc. We put these features into an equation and produced a price. Any change in any feature resulted in a direct change in the price. In contrast, classification problems have a discrete set of values such as small, medium, or large, 1 to 100, 101 to 200, 201 to 300, or true and false. changes in the feature values may or may not change the classification. So what type of problem do we have? Again, the solution statement comes to our aid. From the solution statement, we see that the algorithm must predict which people are likely to develop diabetes. Remember, diabetes is true or false, and therefore diabetes is a binary outcome. Since we are predicting a binary outcome, diabetes or not, we can eliminate any algorithms that do not support classification in general and binary classification in particular. That disqualified some more algorithms, but perhaps not as many as you might have thought. This is because many algorithms support both regression and classification. We are down to 20 algorithms, but that is still too many. Since this is our initial algorithm, let's keep it simple. Let's also eliminate algorithms that are ensemble algorithms. These are special algorithms that combine multiple algorithms under one interface. These algorithms are more often used when we need to tune a model to increase performance, and we are still trying to do our initial training. Also, ensemble algorithms tend to be complex and difficult to diagnose and troubleshoot when the results start going awry. We still have a few algorithms left, and we can divide these into two groups, basic and enhanced. Enhanced algorithms are variation on basic algorithms. They have been enhanced to perform better and/or add additional functionality. As a result, they are more complex to understand and use properly. Since this is our initial algorithm, let's stick to the basic algorithms. These have the advantage of being less complex and therefore easier to understand. For our problem, let's look at 3 basic algorithms as possibilities for use in our initial training and evaluation. We will look at naive Bayes, logistics regression, and decision tree. Each of these algorithms are classic machine learning algorithms, and understanding a little bit about each one can greatly help in understanding more complex algorithms that use these algorithms as building blocks. The naive Bayes algorithm is based on Bayes' theorem. This theorem calculates the probability of diabetes by looking at the likelihood of diabetes based on previous data, combined with the probability of diabetes on nearby feature values. In other words, so how often does the person having high blood pressure correlate to diabetes? It makes the naive assumption that all of the features we pass in are independent of each other and equally impact the result. For our data, this means that blood pressure is as important as BMI, which is also as important as the number of pregnancies. This assumption that every feature is independent to the others allows for fast convergence, and therefore requires a small amount of data to train. The logistics regression algorithm has a somewhat confusing name. In statistics, regression often implies continuous values, but logistics regression returns a binary result. The algorithm measures the relationship of each features and weights them based on their impact on the result. The resultant value is mapped against a curve with 2 values, 1 and 0, which is equivalent to diabetes or no diabetes in our case. The decision tree algorithm can be nicely visualized. The algorithm uses a binary tree structure, with each node making a decision based upon the values of the feature. At each node, the feature value causes us to go down one path or another. A lot of data may be required to find the value which defines taking one path or another. As we see, decision trees have the advantage of having tools available to produce a picture of the tree. This makes it easy to follow along and visualize how the trained model works. From these 3, let's select naive Bayes as the initial algorithm for training and evaluation. Naive Bayes has a number of characteristics that make it useful as an initial algorithm. First, it is simple to understand. It uses how often a feature is associated with the result to determine if the value is diabetes or not diabetes. Second, the algorithm is fast. Training time of some of the more complex algorithms can run 100 times or more longer. And in machine learning, you often have repeated cycles of running the algorithm, evaluating the result, and tweaking the data. Having a fast algorithm makes these cycles much quicker. Finally, the algorithm is stable. With some algorithms, as you work with the data, small changes in training parameters cause the results to vary widely, or worse, the algorithm fails and returns nonsensical results. Both of these can send you on a long and frustrating debugging cycle. Naive Bayes does not exhibit these behaviors. So let's summarize our algorithm selection process. First, we need to acknowledge that there are a lot of algorithms available and more being created every day. With all these algorithms available, we need to select one we will initially train with our data into a model. To select this algorithm, we can use the features of our problem that we captured when we defined our solution statement. From the solution statement, we know we have a supervised machine learning problem which removes all of the unsupervised machine learning algorithms. We wanted binary results, not continuous values, which further reduces the number of viable algorithms. Since this is initial algorithm training and evaluation, we also eliminated all ensemble algorithms that combine multiple algorithms. We also decided that for initial training, we only wanted basic versions of the algorithms. After evaluating the basic algorithms, we selected Naive Bayes as our initial algorithm because it is fast, simple, and stable. In the next sections, we will train this algorithm and see how well it can predict if a person is likely to develop diabetes. In the previous modules, we covered the workflow steps of asking the right question, where we defined our solution statement, preparing data, in which we obtained raw data and transformed it into the data we will use for training, and selecting the algorithm, where we selected the initial algorithm we will train and evaluate. In this module, we'll put the pieces together and train the algorithm we selected with the data we prepared. When we are done with this training process, we will have a model that can predict if a person is likely to develop diabetes. In this module, we will get a detailed understanding of the training process, introduce the scikit-learn library, which can make the training and evaluation process much easier. Then we will go back to Python and train our algorithm with our diabetes data and produce a trained model. A good definition of machine learning training is letting specific data teach a machine learning algorithm to create a specific prediction model. Notice the use of the term specific. Data drives the training, and if the data changes over time or new data is used, in many cases we need to retrain. And we want to retrain if the data changes. Retraining will ensure that our model can take advantage of the new data to make better predictions, and also verify the algorithms can still create a high-performance model with the new data. Now let's dive deeper into the machine learning training process. Let's review the supervised machine learning training tasks we need to perform. First, we split the prepared diabetes data into two data sets, one for training the model and one for testing the trained model. About 70% of the data goes into the training set and about 30% goes into the testing set. Then we train the algorithm with the training data and hold the test data aside for evaluation. This training process produces a trained model based on the logic in the algorithm and the values of the features in the training data. But what does this training process look like? To make this more concrete, let's take a look at a hypothetical training session of some hypothetical disease data. Note, this is just an example. I am not using our diabetes data in these plots. We are trying to understand if a person is likely to develop a disease based on a set of health test results. In machine learning, these test results are the features. Let's plot two of these features, feature X and feature Y, and the disease results from our hypothetical test data. We show not disease as blue circles and disease as red X's. When we train, we expose code in the algorithm to data with which it interacts. This creates a model whose parameters are set by the feature values to define the boundary between the disease and not disease results. We call this the decision boundary. The key point is the structure of this boundary is defined by the combination of the algorithm and the training data, which adjusts the model's parameters. As you can imagine, this relationship can get quite complex. Also notice that the training boundary is not perfect. That is, we see some blue circles in the red X side and vice versa. We will talk about this later, but for now, know that perfect accuracy against training data is not the goal. The goal is accuracy against real-world data. So now we understand what we use our training data for. But I bet you're thinking, what about the test data? Why are we only using the training data to train? What are we going to do with the test data? You are correct to question this. Any thoughts on why we split the data and then only used one of the sets of data in training? Well, if we used all of the data to train, the produced model would be trained with both training and test data sets. Since data drives training of the model, this additional data would impact the workings of the model. Also, when we evaluated the model with this test data, it would likely falsely perform well since the model has seen the data before and knows about the test data's biases. But the model could perform poorly when we use real-world data that has a different set of biases. To prevent us from being lulled into thinking that the model performs better than it really does, we need some real-world data to test against. We used the previously unseen test data as the stand-in for real-world data, and since our data comes from the real-world data, using the test data, we are testing against a set of real-world data. We are just about ready to train our algorithm and create the trained model. But before we get started training, we need to select the features we will train with. Since data drives how the model is trained, we want to ensure that we only train with the minimum number of features. This makes the training go faster and often more accurately. We can look at the data and reason about the context of the problem to make our selection. When I reviewed the features, it looks like now that we have tidied up the data, we can use all of the fields we have remaining. Now that we understand in detail how to do the training, we're just about ready to code. But before we start coding, let me ask you a question. Do you usually write all your code from scratch? I bet not. I bet most of the time you're like me and will try to find a library that can do some of the repetitive tasks for you. In Python, there is such a library for handling machine learning training and evaluation tasks. The library is called scikit-learn. Scikit-learn provides a set of simple and efficient tools that can handle many of the tasks we routinely perform in machine learning. Let's take a look at the scikit-learn library and see how it can lessen our workload. As the name scikit-learn implies, scikit-learn's purpose is to support machine learning. Scikit-learn is built on oft-used Python libraries such as NumPy, SciPy, and matplotlib, and supports these and pandas data frames. The scikit-learn library is a tool set that makes it easier to perform training and evaluation tasks such as splitting the data into training and test sets, preprocessing data before we train with it, selecting which features of the data are most important, creating our trained models, tuning the model for better performance, and a number of other common tasks. In addition to these features, the library provides a common interface for accessing algorithms. And now that we know about scikit-learn, let's see it in action as we split our data and train our model. Let's go into Jupyter Notebook, where we will split our data into training and test data sets, perform any required post-split data preparation, and train our initial algorithm with our training data. Now that we have our data in a form we can use, we can split the data into training and test sets. We will train our algorithm with the training set, and we will use the test set to verify the quality of the training. We will never use the test set for training. To do so would train the model to the features in the test set and invalidate any testing performed with this test data. Scikit-learn contains the train test split method, which makes it easy to split the data. We use this method to split our data with 70% being put in the training set and 30% into the test set. We start by importing the train test split method. Next, we define lists of the feature columns and the predicted column, diabetes. We split our prepared data into two data frames, one containing the feature columns and the other with the predicted diabetes result for each observation row. These data frames and the test size, 0.30 for 30%, are passed to the train test split function. Train test split splits the original data frames and returns 4 NumPy arrays of data. The arrays contain the values of the test and training feature columns and the test and training diabetes result. A minor but important feature is that we set random state to 42. This sets the seed for the random number generator used as part of the splitting process. Setting the seed to a constant ensures that if we run the function again, the split will be identical. Any number can be used for random state. Once the function is run, we have our data split into training and test sets. By the way, we prefixed variable names with x and y, since in algebra it is common practice to say y equals f of x, which means that the result is a function of the features. We need to ensure that we have the desired 70-30% split. These numbers are very close to the 70-30% split of training to test data we desired. However, while the number of rows in the training and test data sets look correct, this is insufficient to ensure that we have the data split correctly. We also need to ensure that the ratio of true and false cases of diabetes in the test and training data sets is the same. We can verify the percentage of true versus false in the training and test data sets match those in the original data. We do this by checking the percentage of rows with diabetes equals 0 versus the percentage of rows with diabetes equal 1. As we see, the percentage of rows with diabetes equals 0 and the percentage of rows of diabetes equals 1 was preserved when we split the data. Therefore, we can move forward with the test and training data sets. Once we have the data split into training and test sets, we may need to do some initial data preparation, which includes some data transformations. However, unlike our early data preparation steps, we will separately apply the transformations to the training and test data sets. This will ensure that the separation between training and test data is maintained. Previously, we checked the data for null values by using the isNull function and did not find any null values. But is this really true? Sometimes null values can be hiding in plain sight. Let's take another look at the head of our data frame. Notice the thickness is 0 in the third row. Having a skin thickness of 0 is not physically possible. This is a hidden missing value. Likely somewhere along the way, 0 was entered for the missing values. Do we have other hidden missing values? Let's check the other columns that might have 0 values to indicate missing data. Wow, we have a lot of columns with 0 values. Which rows are really an issue and which could validly have 0? This is where a little domain expertise can come in handy. Unfortunately, I'm not a doctor or a medical researcher, so we will have to make do with the next best thing, the internet. Doing a few Google searches reveals that of these fields with 0, only one insulin might have a valid 0 value, and even in this, 0 is likely not correct. So now the question is, what do we do about this missing data? Missing data is a common problem, and we have a few options on how to deal with them. We could ignore the missing values, that is, do nothing, delete all the rows with missing values, or replace the missing values with another value. Let's look at the numbers for some guidance. We have 768 rows. Of these, 374 are missing insulin readings. Can we ignore the fact that all this data is missing values? Maybe, but all those 0 values will cause a bias. How about deleting the rows with 0 values? That might be okay for just a few rows, but we probably don't want to delete half our data. Therefore, we need to look at replacing those values with something else. This is called imputing. Imputing is a common practice for handling missing data. With imputing, we have a couple of options. We could replace the 0 fields with their mean, median, or other statistic for the column. Another, perhaps better option is to replace the value with a new value derived from the remaining features in the row as determined by an expert medical researcher. Again, since I'm not a doctor or an expert medical researcher, I don't know how to derive reasonable numbers for each of the missing features based on the values of the other features. So we'll go with another method, using the mean of the column. Using the mean of the column is a responsible tact since it reinforces what data we already have. Scikit-learn contains an imputer class that makes it very easy to impute data, and the imputer class already supports mean-based imputation. Let's import the imputer class. Here we create a new imputer object and specify that it should replace the missing value 0 with the mean for all values on the axis 0, which is column. We use the imputer's fit transform function to create a new NumPy array with any feature value of 0 replaced by the mean for the column. We do this for both the training and test feature value. Note that we must compute this mean separately for training and test data since the values for the features and therefore the means for each data set are different. Now that we have dealt with the zeros in the data, we are ready to train our initial algorithm, naive Bayes. Before we train with the naive Bayes algorithm, we need to import it. In the case of naive Bayes, there are multiple implementation algorithms. We are using the Gaussian algorithm that assumes that the feature data is distributed in Gaussian, which looks like the classic bell curve with most of the data near the mean. Then we call the fit method to create a model trained with the training data. And that's it. The naive Bayes model has been created and trained. Let's briefly summarize what we did in this module. We started with an overview of the training process. This provided us with an understanding of the task we needed to do to split the data into training and test data sets and create a trained model. We then went into Python and split our data and trained our model. To help us with some tasks, we use the scikit-learn library. This library comes with functions that make it easy to split the data into training and test data sets and then train the model. We also discovered that we had a lot of missing data. We discussed this and decided to use mean imputation to replace the missing values. Once we dealt with the missing data, we created and trained the naive Bayes model with our training data. Join me in the next module where we will evaluate the performance of this newly trained model. In the previous modules, we went through the workflow steps of defining our solution statement, getting the data, and selecting an initial algorithm. In the last module, we trained our initial algorithm with our training data and produced a trained naive Bayes model. In this module, we will evaluate this trained model and see how well it can predict the likelihood of a person developing diabetes. We will evaluate our trained model by using a set of test data. Remember, this test data was not used to train the model, so it should give us an accurate evaluation of the real-world performance of our model. This evaluation will provide us with a series of results that we can use to decide if the performance of the model is acceptable. The results will also give us some ideas on how we might revise the workflow steps to improve the performance. Throughout our evaluation process, we need to keep in mind that statistics only provide us data. We are the ones that interpret this data and decide if it is good or bad, and we need to define good or bad in the context of how we will use our model. But enough theory for now. Let's go back to Python and evaluate the model. Now that we have a training model, let's see how well it can predict values. We do this by passing feature data to the model's predict function. The predict function will return an array of 1 and 0s representing true and false. Let's first predict against the training data. Xtrain is the training feature data we use to train the model. To see the accuracy, we load the scikit-learn metrics library. Metrics has methods that let us get the statistics on the model's predictive performance. We are getting over 75% accuracy against the training data. Now let's see how our naive Bayes model performs on the testing data. The accuracy looks good. We have greater than 70% accuracy. Wasn't that our goal? Let's take a look at the numbers in more detail before we declare victory. We can get more details on exactly how this accuracy number was derived if we look at the interestingly named confusion matrix. We'll also take a look at the classification report, which calculates some other performance statistics. The confusion matrix provides a matrix that compares a predicted and actual result for diabetes. The columns are the predicted values. The left column is predicted false, the right column is predicted true. The rows are the actual values. The top row is actual false, the bottom row is actual true. Let's label these values with letters so we can use them in equations. Going clockwise from the upper left, Tn is true negative, actual not diabetes, and predicted to be not diabetes. Fp is false positive, actual not diabetes, but predicted to be diabetes. Tp is true positive, actual diabetes, and predicted to be diabetes. Fn is false negative, actual diabetes, but predicted to be not diabetes. Note that these are the default position for scikit-learn's confusion matrix function. These positions can be altered by using the function's labels parameter. Also, the values position may not be the same in a different language or library. Be sure you review the appropriate documentation for the details. A perfect classifier that classifies everything correctly would return true positive equals 80, true negative equals 151, false negative equals 0, and false positive equals 0. As you can see, our classifier is far from perfect. But is it good enough to meet our problem statement's goal of predicting with 70% or greater accuracy which people are likely to develop diabetes? To see this, we need to calculate some statistics, or rather, have scikit-learn calculate some statistics for us. That is why we added the classification report. The classification reports generate statistics based on the values shown in the confusion matrix. Based on our problem statement, we want to focus on the probability of a true result, meaning the patient has the disease. This is the recall for class 1 or diabetes. Recall is also known as the true positive rate and sensitivity. It is how well the model is predicting diabetes when the result is actually diabetes. Mathematically, recall equals the true positive divided by the sum of the true positive plus the false negative. We are currently at 0.65 or 65%. We need to get this number to be greater than or equal to 70%. Precision is also known as the positive predictor value. This is how often the patient actually had diabetes when the model said they would. Mathematically, precision equals true positive divided by true positive plus false positive. We would also like to increase this number, since that would mean fewer false positives. We have several options for improving performance. We could try adjusting the current algorithm. Often algorithms have special parameters called hyperparameters that let us tune the model's performance. Unfortunately, the naive Bayes model has no hyperparameters. Or we could go back to preparing the data and get additional data or try improving the data we have. But we are using all the data in the PIMA dataset and have already processed it quite a bit. Another option would be to improve how we train the data. We'll revisit this option later, but for now, let's not do this. The final option is to select a new algorithm that works better with our data. But which algorithm? In general, simple is better, but powerful algorithms can make doing a lot of work simple. So let's try random forest. Random forest is an ensemble algorithm. It's based on decision trees. It creates multiple trees, hence the forest part of the name, with random subsets of the training data. The results of these trees are averaged. This usually results in improved performance and can reduce the tree algorithm's tendencies to overfit. We'll talk more about overfitting soon. So let's go back to our notebook and train and evaluate the random forest algorithm with our data. Now let's train the random forest model. We import the random forest classifier and train the model. As before, let's check the accuracy on the training data. Wow! Nearly perfect accuracy with the training data. Let's see how it does on the test data. 71%. That is a big drop in accuracy from the training data. Also, the recall is low at 54%. Something is happening. Notice the accuracy with training data is near perfect, 0.987, 99%, and with the test data is considerably worse, 0.71, 71%. Whenever you see differences as big, you are seeing the classic signs of an algorithm that is overfitting the training data. That is, the model has learned the training data too well. The algorithms we use are powerful and can sometimes be too powerful and too accurate. They learn the training data too well. Suppose we have this data distribution. The red X represents positive values and the blue circle negative values. We train our algorithm with this data. The algorithm analyzes the data and trains itself to create a high mathematical order model based on the data. The exact values of this equation do not matter, but notice the x2 cubed and the x3 to the 8th feature values. These high-order terms let this equation define a precise decision boundary between the positive and negative values. But as a result, the training process has created a model that works very well on training data, but poorly when asked to predict values based on data it is not trained on. This is the classic overfit problem, and is an issue that must be handled to create machine learning models that work well not only on the training data, but also on real-world data. There are two primary techniques used to handle overfitting. Algorithms often have special tuning parameters called hyperparameters. Using these hyperparameters, we can define how the algorithm learns and operates. The hyperparameter that impacts overfitting goes by different names, but the general term regularization is common. Setting the value of the regularization hyperparameter allows the developer to control how much the algorithm focuses on precisely fitting every corner case of the training data. In this equation, the lambda term is an example of a regularization hyperparameter. Different settings for lambda define how much values produced in the trained model are dampened via the regularization term. This dampening decreases the accuracy of the model on trained data, but potentially increases the accuracy of the trained model on new data. Many algorithms have regularization parameters, and each algorithm reacts differently to the data and to the values of its hyperparameters, like those controlling regularization. Some experimentation is required to get the best values for each hyperparameter with a specific set of data. You may have also noticed that the effect of regularization in this particular example equation is larger when the value of the regularization is smaller. This inverse relationship is common, but by no means universal. Be sure to read the documentation of your algorithm carefully to ensure you understand how the regularization hyperparameter works in your selected algorithm. Another solution to overfitting is through a process called cross-validation. This is where we use multiple subsets of the training data during the training process. We will discuss cross-validation in detail later. Also, the use of regularization and cross-validation are not mutually exclusive. Both can be used at the same time. With these options, we are trying to come up with a compromise between accuracy with training data and accuracy with testing and real-world data. This is often called the bias-variance trade-off, and is something we must consider in almost all supervised machine learning algorithms. The end result is that we need to sacrifice some perfection in training for better overall performance with test and real-world data. Let's review and evaluate our options for further performance improvement. We could try adjusting the current algorithm, but the random forest hyperparameter that is likely to impact overfitting is OB score equals true, and we do not have enough data to use that. Getting more data is one of the best ways to help random forests not overfit, but we are already using all the data in the PIMA study. We could try improving the training by using cross-validation, but that does not always have as much of an impact with random forests, since the algorithm is essentially doing cross-validation by building multiple trees and comparing them. Finally, we could switch algorithms, but to what algorithm? We went from the simple naive Bayes to a more powerful Ensemble algorithm, random forest. However, we also discussed going with a simpler algorithm. Let's do that now. Let's use one of the basic algorithms, logistic regression. Logistic regression is simple in form, but turns out to work quite well in many classification scenarios. Let's try logistic regression, and if we detect overfitting, see if we can adjust its hyperparameters to compensate. As usual, we start by importing logistics regression. In the constructor, we set C, the regularization hyperparameter, to 0.7 as a starting guess. Then we train our algorithm. And then we evaluate the algorithm against the test data. Finally, we print the results. The scores look promising, but we are still not achieving the recall score we want. Is there some way to automate selecting the value of the regularization parameter? How about a loop which selects the regularization parameter that returns the highest recall? This while loop will try C values from 0 to 4.9 in increments of 0.1. For each C value, its logistics regression object is created and trained with the training data, and then used to predict the test results. Each test's recall score is computed, and the highest recall score is recorded. That score is used to get the C value that produced the highest recall score. We also plot the recall scores versus regularization value so that we can get an idea of how recall changes with different regularization values. We are still not getting a recall over 70%. What else can we try? Remember, our data had more non-diabetes results than diabetes results. Perhaps this imbalance is causing an issue. Unbalanced classes are very common in datasets. They occur when we have more than one class result, diabetes versus not diabetes in our data, than the other. If you remember from our earlier work, 65% of our results are not diabetes and 35% are diabetes. This imbalance in the class can decrease the performance of an algorithm. Luckily, some algorithm implementations, including logistics regression and scikit-learn, include a hyperparameter that instructs the algorithm to compensate for the class imbalance. This is equivalent to balancing a scale, and the result is a shift in the predicted class boundary. Let's enable this hyperparameter in our model and see if it fixes the class imbalance and, more importantly, improves our model's predictive capabilities. Let's repeat the steps we did before, but this time with balanced classes. We start by executing the loop to find the best value of C, the regularization hyperparameter. But this time we also pass the class weight equals balanced hyperparameter. Now we do logistics regression just as before with two changes. First, we set the C value to the best score from the loop above, and second, we include the class weight equals balanced hyperparameter. Let's see how these changes impact the recall score. Wow, we are successful. We achieved our goal of 70% or greater accuracy in predicting diabetes. I guess we are all done. But we have only tested this on one set of test data, and by looping through the values, we sort of cheated by setting the regularization value based on the test data. Is there some way we could test on more data and ensure that we have the algorithm tuned to perform well on a wide set of data? Of course there is, but we may trade off some performance on the test set for better performance on a wider set of data. We previously mentioned cross-validation in reference to handling overfitting, but cross-validation can do so much more. By now, you are familiar with the training-test split we have used to divide our data into training and test datasets. We always hold the testing data set in reserve to test the model's predictive capabilities. As we try to improve performance of the model, we make adjustments to the model and retest the model's performance with the test data. However, there is a danger in this approach. We are starting to let the checking of accuracy with the test data affect our result. Thus, we are suddenly tuning the model to the test data. However, we need some sort of data to help us tune hyperparameters. It would be great to be able to hold the test data aside and only use it for final testing and have some other data for tuning. Where can we get this other data we can use for tuning? One approach is to go back and resplit our data into 3 datasets: training, validation, and testing. We use the validation set to tune and validate our model and only use the testing data for a final test. This is a common technique, but has a couple of issues. First, how do we choose the validation set? We want the best validation data. We could just resplit the set to say 50% training, 25% validation, and 25% testing. But sometimes, like in our data, we don't have a lot of extra data. Also, does this address the issue of overtraining? Maybe, depending on the data. But there is a better alternative. Let's talk about cross-validation, and not just any cross-validation, k-fold cross-validation. With k-fold cross-validation, we do not use the testing data for evaluation. We split our training data into n folds, each of the same size. We then select one fold to be the validation set. We make the other folds the training set. We train the algorithm on the training set and evaluate it with a fold that is the validation set. We repeat the training and evaluation with the second fold as the validation set, and then again and again until each of the folds has been used as the validation data. The result of each loop through a fold is a set of values for each parameter and associated scores for the accuracy and other performance metrics. This k-fold structure provides the capability to generate multiple values with which to tune the hyperparameters. A routine can be written to determine the best value of a hyperparameter, such as regularization, for each fold. When all of the folds have been processed, the hyperparameter for the model can be set to the average of the fold's best hyperparameter values. This provides the model with a hyperparameter that may not perform best on a specific fold or other subset of data, but in general performs well on all data. We can use the scikit-learn cross-validation library to access the cross-validation methods that make it easy to perform k-fold cross-validation. Then you would need to add code to handle determining the best hyperparameter value for each fold, and then train the model with the average of the best hyperparameter values. But wouldn't it be great to use a model that did all this work for us? We can. Scikit-learn provides special Ensemble versions of the algorithms that contain the code to determine the optimal hyperparameter value and set the model to that value. Scikit-learn has a series of classes that implement variants of the algorithms with the use of cross-validation to determine hyperparameters built in. The naming convention for them is the base class name plus capital CV. Just like other predictor classes, they implement fit, predictor, and other methods that you have seen before. You can use the parameters in the constructor to specify things such as the number of folds, and then when you run fit, k-fold validation is run with the specified number of folds on the training data. Other parameters in the constructor let you define how the optimal value for hyperparameters, such as regularization, is determined. How cool is that? The bottom line is that you can use these CV variants just like their non-CV variants. However, they take a little longer to run since they are doing certain operations multiple times. Since we previously used logistic regression, let's add cross-validation to it. Scikit-learn has an Ensemble algorithm that combines logistic regression with k-fold cross-validation in one easy-to-use interface. This is the logistics regression CV class. Let's use this now and see how easy it is to incorporate cross-validation with logistics regression. As expected, we first have to import the logistics regression CV library, and then we invoke the constructor to create our object. All of the splitting of data and training and evaluation cycles performed in cross-validation can be compute-intensive. We need to take advantage of all the resources our system can provide. We do this by setting the parameter n_jobs to -1 to tell the application to use all the cores on our system. We also set the number of folds to 10. We then set the CS param to 3. The CS params documentation say that setting it to an integer value defines the number of values it will trying to find the best value for the regularization parameter for each fold. Wow, notice all the parameters available. Ensemble algorithms like logistics regression CV have a lot of parameters. That's a lot of settings one could play with. Now let's predict on test data. Our recall score is not quite what we achieved by tuning the score against the test data, but by using cross-validation we will likely score better on real-world data. Also remember that with these Ensemble algorithms there are a lot of parameters that we can adjust, and some are quite powerful. With all these parameters, it is likely that some combination of settings will push the scores even higher. but I will leave playing with these parameters as an exercise for you. Just know that with performance improvement, sometimes the hardest thing is to know when to stop. Or as Edison said, and as we have seen, Edison was so right. In this module, we evaluated the performance of our initial naive Bayes trained model against the data. We did this by using the predict function to generate a prediction of how likely a person was to develop diabetes. We used the confusion matrix and other evaluation functions to review the predictive performance of the model and inform us of areas which needed improvement. We chose to improve the performance by using a different algorithm, random forest. But we ran into issues with overfitting. To handle overfitting, we switched to the logistics regression algorithm which supports regularization. We found that with this algorithm we could meet the performance goals of predicting with 70% or greater accuracy if a person was likely to develop diabetes. But to do this, we had to utilize the test data to tune our regularization hyperparameter. A better solution is to use cross-validation to tune the hyperparameter against multiple subsets of training data. This performed a few % worse on our specific test data, but with real-world data should perform better than a model tuned on a specific set of test data.